else. So let's start. See. So, I have to, no, it's okay. Okay. I start with some definitions. Let's recall that a set in Rn plus 1, we will be all the time in Rn plus 1. So this will be this ambient space, dimension n plus 1. This is called n-rectifiable if there are Lipschitz maps Fi from Rn to Rn plus 1 such that the images of these spaces of the Lipschitz images of Rn cover almost all the set E up to a set of 0 n-dimensional Hausdorff measure, right? This is n-dimensional Hausdorff measure. All right, and this family has to be countable at most. Well, in the last decades, there has been a lot of interest in characterizing and studying rectifiability in terms of different square functions, typically motivated by works in harmonic analysis or because of connection with harmonic analysis and also with PDEs. And these techniques have been applied to study the L2 boundedness of singular integral operators, analytic capacity, harmonic measure, boundary problems, etc. So, and we will be interested here in mostly in a particular square function that was introduced by Bishop and Carleson. I need to talk about tangent points, and I will introduce a careful definition of tangent for sets that are n-rectifiable. It turns out that it is a classical result in geometric measure theory that the set of tangent points for any set E is n-rectifiable. And conversely, if E is n-rectifiable and has finite n-dimensional Hausdorff measure, then at almost all points there exists an approximate tangent hyperplane. Okay.
The first is that take the n set.
Yeah.
And tangent point is the point where there's tangent to something.
Yeah, we will see now. For instance, yeah, I will define now what is tangent in general and what is an approximate tangent. Yeah. So, given a point x in Rn plus 1, first I define a cone and a unit vector u and an aperture parameter a between 0 and 1. We consider this two-sided cone. It's can be written in this way, but it's if you look at the drawing, I think it's most clear. This is a two-sided cone with vertex at x and aperture a equals to cosinus of theta, and u is the x of the cone. Then we say that an open set, well, we introduce tangents to open sets. Given an open set, but this wouldn't make sense for any set. Given an open set omega and a point x in the boundary, we say that the boundary has a tangent in x if there exists a vector u. The vector u will be the normal vector to the tangent, such that for all apertures between 0 and 1, there exists some radius depending on the aperture, such that the boundary of omega intersected with the cone and intersected with this ball is empty. That is, if we put here a circle with radius r, the boundary should be away from the cone. And for any aperture as large as we want, if here we're saying that we find a radius as small as required, such that the boundary will be out of this cone. In the particular case of open sets, we ask an additional condition that perhaps is not very standard, but I think it's appropriate for this talk. This additional condition is that one component of, when we put here a circle, one component of this cone intersected with the circle is contained in omega, and the other component is contained in the complementary domain. For instance, you can think about Jordan domains, and then one asks, or we will ask that one of these cones, one-sided cone, is contained in the domain, and the other in the other Jordan domain. All right. By the way, the notion of approximate tangent for approximate tangents, we ask the approximate tangent. We ask, instead of asking this set to be empty, we ask this limit, these measures to tend to zero. Of course, this makes sense or is interesting when the set has, for example, locally finite n-dimensional Hausdorff measure. So this is, of course, the notion of tangent is stronger than the one of approximate tangent. All right. It turns out that any set that is n-rectifiable and has a finite surface measure has approximate tangents. Any set putting delta omega instead of any set. All right. Let's talk now about Carleson's epsilon square conjecture in the plane. So in this case, omega will be a Jordan domain. So we consider a Jordan curve gamma and omega 1 and omega 2 are the bounded and unbounded components of the complementary of the curve. And then we consider a point in the curves and some radius, and we denote by I1 and I2 XR the longest arcs contained in omega 1 intersected with this sphere and omega 2 intersected with this sphere circumference. That is, imagine that we have this drawing, then we have X point in this Jordan curve, and then here I1 is this arc that is contained in omega 1, and I2 is this arc in a circumference of radius r. And in this case, there are two candidates for I1, this one or this one, and two candidates for I2, this one or this one, and we take the longest ones. All right. Then we consider a little coefficient epsilon xr that measures how far is this, or how close are these angles corresponding to these arcs, how close they are to be plane angle. So they are just the maximum of the difference between p minus theta 1 and p minus theta 2, everything in modulus. So that if these angles are plane, then this coefficient is 0, right? So imagine that, well, no, the opposite. Yeah, imagine that we have a curve that is in some part, a curve that goes here. So of course, in this part of the curve, this coefficient epsilon xr is equal to 0. Because this angle is plane and this angle is. So these coefficients measure how flat is the curve in a sense. And then what we do is we consider here, we consider this integral. We integrate from 0 to 1 these epsilon coefficients to the power 2, and we integrate dr over r. So this is a scale invariant integral, right? Epsilon is invariant by scaling, and also this integral is essentially invariant by scaling. Then, in a joint work with Benjamin and Keleville in 2021, we proved the result, which was known as Carleson's conjecture. The result asserts that if we have a Jordan curve, which may have infinite length, it could be, for example, like some kind of snowflake, then up to set of 0 length, and one-dimensional Hausdorff measure for me is the same as length. This epsilon, the points where this square function, we call this a square function. It's a function that depends on x, and well, we call it typical square because there is a square here inside. And so this square function is finite if and only if omega has a tangent in this point. So except for a set of 0 points, this is an implication, a double implication. So one characterizes existence of tangents in terms of this analytic property. Let me say that this was conjectured by Carleson all in because of some connections and some result that appearing in connection with the study of harmonic measure and some estimate due to Berlin. Well, this was conjectured in the late 80s, and we proved sometime later. Let me say also that this implication is showing that at tangent points, this square function is finite, except for sets of 0 length. And I will say a few words about this. This was shown by Chris Bishop. And the opposite implication is the most difficult one, that is the one solved in this theorem. So in this slide, I introduce a new coefficients and that are useful to solve the easy direction of Carleson's conjecture. So given a set E in the plane and a ball B, we consider this beta coefficient of this ball B. This is a beta coefficient that was introduced by Peter Jones when studying an analytic version of the Darling-Seltman theorem in the plane. And well, this is equal to this thing here. So we have a set in the plane, and then we take the infimum over all lines of this supremum. This is the supremum of x in the x belonging to intersected B. So it could be here. We take this. Then we take the distance from this from the points x in E to the line L, and we divide by the radius of B. But essentially, this is just, after a moment of reading, you can check that this quantity here is equal to the width, or maybe 1/2 of the width of the thinnest strip that contains E inside this ball. So that if this set is contained in a line, this coefficient will be 0. And on
the line, not through the origin?
No, not necessarily. Here it looks in the origin, but maybe it's slightly, yeah.
Okay.
Not necessarily. Not necessarily. But in this coefficient, yes. And in fact, let me say that it is easy to check that the epsilon coefficient is smaller than the beta coefficient. But for instance, there could be like curves like this one, such that the epsilon coefficient, remember, that measures how far is this angle from being a plane angle and how far is this from being a plane angle. So if we have a curve such as this one, the epsilon coefficient is 0, but the beta coefficient no, because of course the thinnest strip containing this has positive width. So betas are some interesting coefficients that are larger than the epsilon coefficients. Yeah, yeah. But of course, the only interesting lines are the ones that, for example, that are close to at modulo some constant. One can assume that the lines intersect the point E, the set E. So there is no restriction in assuming that the lines intersect the point. So then there is this theorem due to Bishop and Jones that is appears like a corollary, not easy corollary, as a previous result of Jones, that is the so-called traveling sigma theorem of Jones. And it asserts that if we have a Jordan curve, then up to set of zero length, the finiteness of this integral is equivalent to the existence of a tangent at x. Not approximate tangent, but a true tangent. So this is the same equivalence we had previously with epsilon coefficients instead of beta coefficients. So Carleson conjecture stated that the same was true with epsilon. So then what we have is that, since I already said that the epsilons are smaller than the betas, this is a quick calculation. Then if this is finite, if this is the square function associated to the epsilon, then this square function will be also finite, and so then there will be a tangent. So I'm going in the opposite direction. Sorry. Let me say I am going. I argued incorrectly. So let's start. If gamma has a tangent at x, then this integral is finite, and since betas are larger, also the integral corresponding the epsilons will be finite. Sorry. Okay. And so we have shown that the is implication, right? Well, the is taking the preceding result as a black box, it's true that the proof is easy, although proving this is not, it's not trivial. So, and the rest of the talk, I will talk mainly about the other implication and also about a higher dimensional version of this result. So, what happens? About a few words about the proof. About the proof, we use compactness arguments, blow-up arguments, and quantitative rectifiability techniques. Let me say only that. We will say more things later. And then an interesting question that raises is the one about obtaining a version of Carleson's conjecture in higher dimensions. The version for Carleson's conjecture that I stated was for Jordan curves. So, of course, in higher dimensions, it is not clear what could be the replacement of a Jordan curve. So, which open sets should we consider? Which coefficients should we consider? Angles or whatever. So, and then we studied this question with Ian Fleischler and Michele Villa. Names will appear soon. And then, in order to do this, we use this notation. SXR stands for the sphere with center X and the radius R. And then we introduce, well, this given X and radius R, we consider this a half space H, such that X belongs to the boundary of the half space. And then with a note by SH1XR, the sphere intersected with the half space. So this is H. This is this half sphere, and the complementary half sphere is other. So one is this is other. But it's in higher dimensions. So it's and then we consider this quantity. We take the infimum over all half spaces satisfying these conditions, and of this quantity, 1 over the reduced to the power n, and here we put the Hausdorff measure of this half sphere minus omega 1, and here we measure the Hausdorff measure of the other half sphere minus omega 2. So that if one half sphere is fully contained in omega 1 and the other half sphere is fully contained in omega 2, then this coefficient is 0, right? So you see that there is some connection with this coefficient with the previous one. It's not, I'm not saying that this is exactly the same quantity, but there is a connection. Notice that this is an invariant by scaling, right? Because we have n-dimensional measure and we divide by r to the n. Then we proved, this with Michele Villa and Ian Fleschler, Villa, that if we have now two arbitrary, not only Borel set, open set, but just disjoint Borel sets. If we have two disjoint Borel sets, then for any Borel set of the points x such that this square function is finite, that is the place where this function is a square function, this is unrectifiable. We write this saying that any Borel subset of these points implies that this is rectifiable to avoid some measurability conditions. So essentially we have that the finiteness of this square function implies unrectifiability. Then by this thing I stated there, of course, it turns out that if we have that this set that we could call like F, for example, the set where this is finite we could call F, then we would get by the result that there are approximate tangents, but the approximate tangents are not with respect to omega, but with respect to F. Right? So then we could get some, and moreover, from this, that is, we get exists a weak notion of existence of tangents, moreover, only depending on this F. So which is quite far from saying that if omega 1 and omega 2 are open sets, which is very far from saying that we have two tangents, right? All right, but an interesting fact is that we don't require any topological condition apart from being Borel. Again, the proof uses blow-up arguments, and there is a constructive part using Fourier type estimates and corona construction, that some techniques coming from some quantitative rectifiability. And the arguments are more complicated than the ones in the previous result with J and Villa, because the previous results used strongly the connectivity of the boundary. But, okay. But let's go on. Let's talk about the existence of tangent. By the way, another little remark is that here we have one implication. The finiteness of this square function implies rectifiability, but the opposite is not true. It's not true. We can have like sets that are rectifiable, that accumulate somewhere, and where with this square function would be infinite. So this looks a very powerful result because it applies to very general sets, but it's not a double implication. So, okay, so let's just go now to the existence of true tangents. So what about the existence of true tangents when omega 1 and omega 2 are disjoint and open? Then we need these coefficients epsilon n are too weak to get existence of tangents, as we have seen, but by what I told you, and then we require some new definition, some new coefficients. And to motivate the introduction of these new coefficients, I recall what is the Alka-Ferrelli-Fermat monotonicity formula. So it's here there is a long statement. You don't have to remember the whole statement, don't worry. So we have a point x in Rn plus 1, a big radius r, two functions u1 and u2 in this solar space in the ball. They are continuous in the ball. They are non-negative, subharmonic, and they vanish in the center of the ball, and their product is 0. For simplicity, you could think that imagine that you have two domains, omega 1 and omega 2, and you could take like u1 and u2, the green function for one domain, and u2, the green function for the other domain, so that they have disjoint supports, well, except at the moment, right? So imagine the typical application is in this case, u1 and u2, green functions with disjoint domains with the pole far away from this ball. All right, then one consider this product involving this gradient of u1, this product involving this gradient of u2. One can check that this is a scale invariant. It looks well, it's this quantity, this factor is the same as this one, changing u1 by u2. And then it turns out that this jxr is absolutely continuous with respect to r. This is not very surprising, but what is very, very, very interesting and not trivial at all is that this quantity is monotone. In fact, the derivative with respect to r of this jxr is positive, it's not negative. With this jxr is always positive, so going from here to here, this derivative is positive. So this is a monotone quantity. So this is why this formula is called the monotonicity formula of Alka-Ferrelli-Friedman, which has important applications in Fermat-Boundary problems. Moreover, the way how one shows that this is positive is showing that this term here is larger than this. I will define in a moment what is alpha 1 and alpha 2, and then this thing in the parentheses turns out that this is positive. Where alpha 1 and alpha 2 are the characteristic constants of these subsets of the sphere. So sigma I. So we have this sphere, and then imagine that we have here, this is omega 1, this is omega 2, then sigma 1, then this is sigma 2. So this is this part of the sphere. But translated, this sphere has radius x, center x, and radius r. Then we do a dilation and translation so that we put this subset into the unit sphere, right? So it's yeah. Yes.
So the x when one is into a green function, stand up to the component
by zero. By zero, yes. Thank you. Yeah. What are the characteristic constants? Essentially, there are these numbers. So they are whose definition is not geometric. So up to now, everything looked a very geometric measure theory. But what we do is we consider this subset sigma I of the sphere. This is a domain in the sphere, an open set of the sphere. And then we consider the first Dirichlet eigenvalue for this set sigma I. That is, we consider the spherical Laplacian of U, and this equation, the minus spherical Laplacian of U, equal to lambda, this lambda, times U. And then we consider the eigenvalue, this is an eigenvalue, that is minimal, the first one, non-zero. Then the alpha is in the plane, and remember that we are in Rn plus 1. So in the plane, this does not appear, so in the plane, alpha is just the square root of the first eigenvalue. And the higher dimensions, you can think that it's modulo technical details, it behaves as the square root of the first eigenvalue. And then there is a very important inequality proved by Friedland and Hyman many years ago that shows that if you have two disjoint domains in a sphere, like sigma 1 and sigma 2, arbitrary, they don't need to come from anything, then alpha 1 plus alpha 2 minus 2 is positive. And the only case where this is equal to 0 is when we have two half spheres. All right. So now you start to see that perhaps these quantities could be related to these coefficients epsilon, right? All right, let's continue. So we have this, that is, it will turn out that this quantity will measure how far, in fact, sigma 1 and sigma 2 are from being two half spheres. Well, as I already said, the Alka-Friedman formula is useful in free boundary problems and also in particular in free boundary problems where one studies, for example, two phases of the harmonic measure, and the two phases are two disjoint domains. That we will not talk too much about this. Well, what is the connection of these numbers with our epsilon coefficients? Well, Allen Crivens of a new measure in our work about Faber-Krahn inequalities and related things, they realized that at least that when you put sigma I, this imagine that we're in the plane and we consider in the plane this is I1, this is I2, and then well, we identify. Imagine that we are in the unit sphere, so that R is equal to 1 and X is equal to 0. Then in this case, sigma I will be II, right? Imagine that we are in the unit sphere, exist. Then we have that the minimum, well, we have to put here a minimum because otherwise, because this alpha I could tend to infinite if the domains become very, very, very tiny. This alpha I tend to infinite, then one has to elongate. But putting this minimum of 1, and this alpha 1 plus alpha 2 minus 2 is comparable to the square of the epsilon and coefficient of Carleson. This is an easy computation, and it is not difficult to check because in domains in the plane, one can compute domains for spherical domains in the plane essentially are arcs in the sphere, arcs in the circumference. And for arcs in the circumference, one can compute by hand the first eigenfunctions are just sinus of some angles. And then these numbers have to do with the angles corresponding to some arcs, and then an easy computation shows that we have this comparability. So in the plane, saying that the square function of Carleson is finite is equivalent to saying that this quantity here is finite. So in higher dimensions, one can state an equivalent version of, or natural generalization of Carleson conjecture consists in proving that this integral is finite if and only if omega has a tangent at x. For suitable domains, of course, and of course, modulo sets of 0 in dimensional half of measure. And this is what we will do. All right, but before doing this, let me say we have to restrict a little the class of domains, but not too much. So the class of domains that we will consider are the ones that satisfy what one says the CDC. CDC stands for capacity density condition. It's a condition that appears quite often in potential theory. It can be stated in terms of capacity, but also it has an equivalent definition in terms of Hausdorff content. So given an open set U, like omega 1, an open set U, we say that this satisfies the capacity density condition if there exists some S larger than n minus 1. Remember that we are in Rn plus 1, so this is codimension 2. there is some S such as this one, such that this the Hausdorff content of this ball minus U is larger than R to the S. So this is a thickness condition of the complementary. So remember that this type of conditions are the ones that are good also to solve the Dirichlet problem. I think in regular domains one also has, it's not in, so in particular this implies being irregular, for example. So this must happen for all x in the boundary and for all radius R. With a uniform constant and for some S fixed. And this condition is equivalent to saying that we have that this capacity is larger than R to the power n minus 1. This is, I will not define this capacity now. It's the Newtonian capacity associated to the fundamental solution of the Laplacian, the one that has homogeneity minus n minus 1. Okay. Well, then we have the precise result we have proven is this one. We have shown that if we have two domains omega 1 or open sets, disjoint open sets in Rn plus 1, such that their union satisfies the capacity density condition. For example, in the plane we could have omega 1 and omega 2. Then that the union satisfies the capacity density condition. What is the complementary of the union? It's just this curve, the Jordan curve. It is easy to check that the Jordan curve, that is for any point such as here, the complementary is the curve, and by continuity, this will be comparable to R. This condition will be true for Jordan curves with S equal 1 and with S equal 1. So Jordan domain satisfy this condition. Anyway, for disjoint, if we have two domains satisfying such that the union satisfies the capacity density condition at two sets of 0 n-dimensional Hausdorff measure x, and for a point x that belonging to the common boundary, this is a tangent point both for omega 1 and omega 2 if and only if this integral, that is the kind of Carleson square function, integrated, is finite. In the plane, yes. In the plane, yes. But what happens with epsilon n? With epsilon n is much more delicate. In the plane, they are comparable. Yeah, in the plane, moreover, they are not angles, and this is what in the rest of the talk I want to talk a little about. So, yeah, of course, one has the way to prove this theorem is we have to relate this analytic condition to something geometric if we want to argue with geometric arguments. But the is implication does not use geometry essentially, because this implication is this one. We could have two open sets. Just being irregular, we don't need the CDC. Being irregular is much weaker. Then let us check that at almost all tangent points, this integral is finite. This is proven using the Alka-Ferrelli-Freeman monotonicity formula applied to the green functions. So we have, remember this formula. This is JXR. Then remember that the Alka-Ferrelli-Freeman monotonicity formula says that this quotient here is larger than this quantity. What we do is just integrate between 0 and 1. So this is the theorem. It was a theorem. Huh? The theorem of Alka-Ferrelli-Freeman, I repeat, said that this thing is smaller than this one. So then when we integrate this is log of Jx1 divided by Jx0. Then what happens is that one can, using some typical estimates relating the green function to harmonic measure, first one can show that this Jx1 is a finite number. It's a finite number, and what requires some little work is to show that Jx0 is positive. And to show that Jx0 is positive, one can use that estimates some harmonic measure that they say that at tangent points, harmonic measure is bounded from below by R to the n. This is a theorem, it's not, so it requires some work. It's not a very deep theorem, but it's non-trivial. So using this one, and then we're done, this is finite. So the geometric part, in a sense, is hidden in this estimate. All right, now let's talk a little more about the opposite implication, and which moreover will use the connection between these new coefficients, alpha 1, alpha 2, and the coefficients epsilon n. So here I repeat again the definition of the eigenvalue. So remember that the smallest eigenvalue of the Laplacian, directly the eigenvalue, so it's defined in this way. We consider this PD, and we consider a function that is in the sublet space vanishing at the boundary of the domain, and then we take the smallest eigenvalue, then it's well defined, it exists, and moreover, it can be found by this identity. This quantity is called Rayleigh quotient. It is an easy computation that is lambda 1 equals this term here. And moreover, something that is very standard and very useful is that the first eigenfunction has constant sign, and moreover, it's very standard in PDEs, and one can assume this to be non-negative, for example. Then the Faber-Krahn inequality is another inequality that asserts that among all open sets with a fixed volume, the ball minimizes the first eigenvalue. By the way, now I'm talking about, to simplify things, I am talking about this PDE in the ambient space Rn+1. Previously, I had talked about this PDE in the sphere. But anyway, let's go to Rn+1, that is more standard. So I repeat that for among sets with the same volume, the ball is the one that minimizes the first eigenvalue. And the same happens in the sphere, replacing this Laplacian by the spherical Laplacian, and then balls, Euclidean balls by spherical balls. This is, and it turns out that this can be quantified, and it has been a subject of intensive investigation from people in PDEs. So, for example, Brasco, De Filippis, and Velichkov, they proved that if omega is open and bounded, then remember that, and they have the same volume, imagine that they have the same volume, then lambda of omega, this is the first eigenvalue of omega, and this is the first eigenvalue of the ball. This is positive, but moreover, this is bounded from below by the infimum of this measure square of the symmetric difference. And the power 2 is sharp. So this is a geometric quantity that measures how much larger is this first eigenvalue from the one of the ball. It's a very nice result. What is an open problem is to compute the exact constant. So there are other estimates in this field where maybe some sharp constants are known, but depending on what you put here in the right-hand side. And there are also people that have, among many people that have studied these quantitative Faber-Krahn inequalities, there are Melas, Hansen, Nadirashvili, and many others. Then other people that later did something else is this one here, Allen-Krivens of Neumayer. They showed essentially the same, but they put here an extra term. And the extra term they put is the integral of this u omega minus ub, and what square. And what is this u omega? U omega is the eigenfunction corresponding to lambda omega, and ub is the eigenfunction corresponding to b extended by 0. So if So if these eigenfunctions are very different, then this quantity is, well, it will be large, and then this will say that this has to be large. And by the way, it turns out all increments of Neumayer also have shown that the same result is true when one considers domains in the sphere, and when one replaces the Laplacian by the spherical Laplacian. So this, although one has to ask the domains not to be too degenerate, that is omega contained in the sphere, but not too small, not degenerating to a point or not to degenerating to the full sphere. Okay, and why is interesting, for example, the result of Allen-Cribens of Neumayer? Consider this domain in the plane. Then remember that the first eigenfunction vanishes at the boundary, and well, here then we have an eigenfunction that vanishes here, and what happens that the eigenfunction corresponding to this domain will be quite different from the eigenfunction corresponding to the same ball minus the slit, right? But then the result of and also the eigenvalue corresponding to this omega will be pretty different from the eigenvalue corresponding to the ball B. I think that it's natural to think that this will happen because this segment is very far from being invisible for the Dirichlet problem. But notice that the symmetric difference in terms of area is 0. So the result of Brasco, De Filippis, and Vilejkov is not useful to estimate this from below. However, the result of Allen-Cribens of Neumayer is useful because the two eigenfunctions will be different. So this term will be non-zero in this case. What happens is that this term there looks very analytical. It seems that it has no geometric information, or it's difficult to translate that into a geometric information. This is what I said. And well, what we have done in some result, in a sense, is to translate the result of Allen-Cribens of Neumayer into something geometric. We have obtained this result that will be useful later in our result about the Carleson conjecture. We have shown that if we have two domains satisfying the CDC, for example, the slit domain, and then lambda omega minus lambda b is larger than some quantity, and here we put some infimum, and here we integrate on b minus omega. So, for example, b minus omega here could be just this segment, right? And then we put here the distance from x to the boundary to the power n minus s. So s is some number smaller than n. You could think that n is equal to n minus 1, for example.
Is s same as in this?
Essentially, yeah. Everything is related, yeah. What happens is that I have stated this in Rn because we will be interested in domains in the sphere. You have, because this will be also in the sphere. Then we can think. But yeah, so the interesting case, you put here s as close to 0 as you want, but at the end, the only s that are useful are the ones that are between n minus 1 and larger than n minus 1. You can think. Okay. Notice that here we put the distance from x to the boundary to the power n minus s. And here we integrate with respect to Hausdorff content. Hausdorff content is not a measure. But anyway, it's not. But you can estimate it. It's defined in this way, in the typical way. And this integral here, for example, here you put if if here you could consider H1 infinity here is comparable to H1 in this case. And here you would be integrating here this distance to the boundary, and this would be with something positive. All right. By the way, I stated this in this way to be more geometric, but we have a version of this theorem in terms of capacities that is I would say, sharper, and does not require the CDC condition. Yeah. Yeah, thank you. 5 minutes, yeah. Okay. Let me say that we cannot replace this by the symmetric difference. It's easy to check. Because in considering domains such as this one, it is easy to check that here we cannot put the symmetric difference. It's only this way. Okay. Some very quick ideas about the proof. I just say that we consider these eigenfunctions. We do a typical trick that is multiplying by this exponential, adding an extra variable. Then we convert, if we do this, we convert eigenfunctions into harmonic functions. So now these U tilde have become harmonic functions in Rn in one dimension more, in Rn plus 1. And why do we like harmonic functions? Because, at least because I am familiar with harmonic measure, and then we have harmonic functions that are positive, moreover, and vanish at the lateral boundary. Remember that these eigenfunctions were positive, so functions that are harmonic and positive are very easy to manage, right? If you are familiar with harmonic functions, then one uses that this UB this is like the green function of this ball. We know very well how this behaves. We know that this is equal to 0. Just very, very quickly. And then we can introduce integrals such as this one, and they behave like such as this one, etc., etc. So it's just to tell you it's not, it's just something that appears in the proof. It's not even the sketch of the proof. All right. And now let's go to the epsilon coefficients, epsilon s. Remember, we introduced epsilon n coefficients. We introduced a variant that is s-dimensional with less dimensions. So again, this is a half sphere, this is another half sphere. Remember, this was the intersect of this half plane, this is the complementary. And then we consider this coefficient. We take this infimum, we integrate in sh1 minus omega 1, sh2 minus omega 2, and this quantity distance from here to here, n minus s. And we integrate with respect to s-dimensional Hausdorff content. It is easy to check that in the case s equal n, we recover the previous coefficient. And when s is equal to n, we have this is equal to 0 and this vanishes. Okay, well, we have proved using that previous theorem about that Faber-Krahn inequality. Using this theorem, we have proven this one, that the epsilon s is bounded by this coefficient, in particular also epsilon n. So these coefficients dominate all epsilon n and also the ones with s less dimension for s between 0 and n. And using this result, then we get that if this is finite, then this is finite. In particular, if this is finite, this is also finite in the case s equal n. But remember that we said that this implied rectifiability. So the finiteness of this quantity in higher dimensions implies rectifiability. But moreover, the existence of tangents requires to working with the coefficients with less dimension, one can recover the result about existence of tangents. So here I'm very fast, just saying that using the full collection of coefficients, we get the existence of tangents. So that's all. Thank you.
Okay, so thank you very much for the very interesting talk. Are there any questions from the audience?
So thanks for the talk. Very interesting. I wanted to ask about some detail that you mentioned briefly. You said you had such a quantitative Faber-Krahn inequality with a capacity
Yes.
error. Could you explain that a little bit more?
Yeah. Yeah, I have to look at that because yeah, it's I can let me look for the definition because it's not. Yeah, it's not. It also integrates, but see if I find. If not, I sketch the idea. If not, it will take some time. Okay, maybe I will tell what you remember otherwise, because the statement is a bit technical. The razor, what is the razor? Here. Yeah. Let me remember. If I remember well, we consider, I think that if I remember well, is that we say that lambda omega minus lambda b, this is larger than, if I think that supremum over all these radius. So this is the radius r, and then we put here radius r. Oops. And then I remember we integrate in here delta b xr, and then I think that we have here. Thank you. Yeah, here we put the capacity of I think it's bx. I think that we take Whitney balls. By, then here it could be like r minus r divided 2, for example. I think it's possibly of intersected with b minus. I think it's something like this, and then normalized in some way. I'm not sure if it is in this one, but something in this spirit. Hn minus 1 y, and then I guess that we normalize something like this. In this spirit. I will show you later, but it's in this way. What we do is to and maybe we wait. Yeah, possibly. I guess maybe there is some weight. I'm not sure. But perhaps here we put. Yeah, maybe it's here putting just in case this. And there is a square somewhere. Possibly, maybe this is a square. I don't remember. Or that is sharp. I will show you later in a few minutes. But it's in this spirit. So we take capacities and then we show this. Then the closer. Yes. There is a factor. I remember involving the distance to the boundary. Yeah, the boundary is the exact. Yeah, because the closer we are to the boundary, some power. The closer to are to the boundary, the smaller is the perturbation. Why? Because, and I think, yeah, it is sharp. Oops. A moment. No. Yeah, like here. the closer we are to the boundary, the smaller is this number. And this is natural also because here, the closest we are to the boundary, the smaller are these functions because they vanish at the boundary. So there are, in terms of this, yeah, it's a formula involving these terms. This is why I don't remember.
Are there any more questions? Well, if not, then let's thank the speaker again.
Thanks.